This is Machine Learning Video Series 2. Here we'll solve traveling salesman problem using machine learning approach. Traveling salesman problem is a classical optimization problem. It tries to find the shortest possible path through a set of n cities, so that each city is visited exactly once. The problem seems very simple, but it is very hard to solve. In our machine learning playground, we implemented two machine learning approaches to solve this problem. One approach uses the genetic algorithm. The other is based on an elastic neural network and self-organization map. Now, let's play with the traveling salesman problem. In your browser, go to ginker.com/AI/genetic algorithm traveling salesman, and then hit enter key. You can see the genetic algorithm can efficiently solves the traveling salesman problem using the default parameters. For crossover, we use the greedy algorithms, which tries to choose the nearest unvisited city as the next move. It can quickly give an effectively short route. The path length is updated at the status bar area. From the input panel, you can see, here, we use a very large population size of 1000. We need to set this parameter large enough to initialize with a rich set of solutions. Some people suggest to use 30 to 60 times of the number of cities. If we use a smaller value, for example, 50, we'll not get a good solution. Here, you see, some routes crosses over themselves. Also note that the path length is longer than previous path with a large population size. We can also try different population sizes. Now, if we click the reload button of the browser, the input panel will be reset to the default values. And the genetic algorithm will try to find the path for the default input data. On the right is the customization panel. In most cases, this panel controls the appearance of the result visualization. Here, the number of cities is controlled by this parameter and the default value is 30. Let's change some parameters here. First, let's change the number of cities to 20, and then click the update button. The optimization starts for 20 cities. Now let's change the city symbol to cross, change the city symbol color to blue. Change line color to purple. Then click the update button. The changes will take effect now. The delay parameter controls the speed of result updating. The default 100 means that the results will be updated once every 100 milliseconds. Now change it to 500 and click the update button. You can see the progress bar updating is much slower. Now let's consider a case with 100 cities. We also need to increase the population size to 5000 and the iteration to 500. Let's also speed up by reducing the delay parameter to 1. Click the update button to see what happens. you can see there are still some path crosses over. And final path length is 8,476. We are certain that this is not shortest route, but is a very good approximation. In order to remove this crossover, people proposed various approaches, such as 2-op swap. Here, we implemented an alternative method to solve this traveling salesman problem. Our approach is based on an elastic neural network plus self-organizing map. Now, hover over the AI drop-down menu and select SOM for traveling salesman. This brings up a new playground window. This is a variation of Cohonan self-organizing map, called an elastic neural network. You can see, the neurons on this network form a ring structure. I have to say here that this approach is not very efficient comparing with the genetic algorithm, but still this approach may be interesting as a self-organizing map application. Here the default optimization is for 30 cities. You can see our neural network and self-organizing map approach indeed solve traveling salesman problem. This is for 30 cities. How about 100 cities? Let's change the number of cities to 100 and change the iteration to 60,000. Usually, we also need to reduce the learning radius for the case with more cities. Here, we change it to 0.05. Click the update button. Let's see what happens. You can see the ring network gradually deforms to fit the traveling route. Now, the optimization is finished. You see the traveling path looks very good, without any crossover. And the final path length is 8,029, is shorter than that from the genetic algorithm. This shows our neural network approach is powerful and useful. Our machine learning playground consists of over 30 machine learning models. If you hover over the AI drop-down menu, you can see all the models. From here, you can select machine learning model and start using them to test your machine learning algorithms. This concludes this video. Thank you for watching.